This is USACO 2020 US Open Contest Silver, Problem 1, Social Distancing. Farmer Jang is worried for the health of his cows after an outbreak of the highly contagious bovine disease, COVID-19. In order to limit transmission of the disease, Farmer Jang's N cows, where N is greater than equal to 2 and less than or equal to 10 to the power 5, have decided to practice social distancing and spread themselves out across the farm. The farm is shaped like a 1D number line with M mutually disjoint intervals in which there are grass for grazing. The cows want to locate themselves at distinct integer points, each covered in grass, so as to maximize the value of D, where D represents the distance between the closest pairs of cows. Please help the cows determine the largest possible value of D. We can take a look at this problem. First, using the sample input. There are 5 cows and 3 grass patches. This means 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. This means that from 0 to 2 is a grass patch. 4 to 7 is a grass patch. And 9, just this one, is a grass patch. And we need to space out 5 cows as much as possible within these grassy fields. The answer is 2, meaning the first cow goes over here, second cow goes over here, third cow goes over here, fourth cow goes over here, and fifth cow goes over here. As you can see, the minimum maximum distance of the cows apart is 2, as seen here and here. And we need to find this value with a quite large data. So we can't find this using brute force, which means we're going to have to use binary search, since binary search can search this in linear time. So instead of getting the answer in n squared, using binary search, we can get this using n, with an n time. To do this, we first need to obviously implement the binary search algorithm, but I am going to skip that step, assuming that everyone watching knows how to implement binary search. But if you don't know how to do this, you can find various tutorials online, and in a nutshell, if we're checking for a wide variety of or a large range of values for the answer, we can first check the middle, and then depending on whether this value worked or not, we can either go to the next half or the previous half, and then find the middle of there, and then the middle of there, and then the middle of there, and then so on and so on until you find the answer. So to implement the method in which we'll check if the value we got from the binary search is correct, we'll first get all of the grassy fields and put it into what should we put it in? We'll put it in a priority queue of a custom class. We'll create a custom class which stores 2 values, int start of the grassy fields, and end. We can implement comparable so that we can sort this and get it in order. And first in the function, we'll iterate through the number of cows, and we'll also keep track of the index of the cows. The first one will start off at the start of the cows dot start, and will plus equals to the value we're checking for. And then we'll check whether this value is within a grassy field. And if not, we'll switch to the next grassy field and then set it to the start of there. If within grassy field, then nothing happens. But else, switch to next grassy field and set index to start of grassy field. And at the end, if we run out of grassy fields, then return false. If no more grassy fields, return false, but otherwise return true. Now we can get to this is my code for the program. First, in the initialization function, I take care of the input and the output. I decided to use a array for it instead of a priority queue because using an array is faster for this case. I took all of the input as long because it can go up to 10 to the power of 18, which can't be stored in an integer. So I got the n, and then the m, and then the m lines of fields, the grassy fields, which I created a custom class for, which has a start and an end, and then I sorted it by the start of the grassy fields so that it's sorted for us to use later. Next is the binary search algorithm. I set the load to 1 since it guaranteed that a solution with d that's greater than 0 is guaranteed to exist. So I put it as 1 and the high to 5 50 times, 5 times 10 to the power of 17, as that's half of the maximum value. And there's at least going to be 2 cows. So the worst case or the best case scenario, the cows can be apart this much. Next is long. Um, this is just a binary search algorithm. Feel free to copy this down if you don't know how to make one. But for it sets the low to middle plus 1, since if this works, we're checking for a higher value, and if it doesn't work, we're setting the high to middle minus 1, since we're going to be checking for a lower value if this doesn't work. And in the check function, we're going to check for whether the apart distance is going to work. And the way I implemented this is I first have a field index which keeps track of which field we're on, which grassy field we're in at the moment. Field is for the actual field itself. Index is where the cow is at, and we're gonna loop through 1 to n. We're gonna set the cow index to the minimum, the lowest value the cows can go, which is going to be the first field's start value. And then we're going to increase by the apart distance. And if this exceeds the end value of field, we're going to keep switching to the next field until our index fits inside of there. And then, of course, if the index is less than the start value of field, we're going to set the index to the field. And when we run out of fields to go to next, we return false, since that means we don't have enough space to fit all of the cows with this much distance. But if we successfully iterate through n while having enough fields, we're going to return true. Now we can submit this on USACO. And it should be all correct.